Welcome back to our lessons on stoichiometry. Today we're going to look at the stoichiometry of methane. What is stoichiometry? Well, if you remember our last lesson, stoichiometry is a discipline of chemistry that involves balancing equations, determining the amount of reactants needed for a chemical reaction, the amount of products made from a chemical reaction. To solve stoichiometry problems, you have to go through several steps, or there's several approaches in solving a stoichiometry problem. In the last video, we used the Big Mac as an example, and you saw the logic approach. The logic approach, remember, we looked at one Big Mac consisting of one hamburger bun, one hamburger patty, one slice of tomato, one slice of cheese, 3 slices of pickle sliced across the width of the pickle, 1 leaf of lettuce, and about a tablespoon of $1,000 dressing, the secret sauce. Now the problem is, how many hamburger patties do you need to make 3 Big Macs? Take a moment to solve this problem. If you remember from last time in the ingredients for making a Big Mac, you should have the answer of 3. Because each Big Mac has only 1 hamburger patty, to make 3 Big Macs, I need 3 hamburger patties. Now let's review a more complex problem we had last time on the Big Mac. I have 18 hamburger patties, 16 hamburger buns, 3 whole tomatoes, a head of lettuce, a jar of pickles, there's about 10 pickles in a jar, a bottle of $1,000 dressing. How many Big Macs can you make? Take a moment to solve this one. Now, if you slice any whole tomatoes, especially large tomatoes, you know, even the small ones, I can get 5 slices on a whole tomato. Larger tomatoes, I can easily get 6 or 7 slices. If I go really thin, I can get even more. So all this should give you an idea. Now, my answer is 16 Big Macs. Why? Well, I can, like I said, squeeze 6 slices easily out of the whole tomato, especially if they're large. So that's 18 there. 18 hamburger patties, a head of lettuce. There's several leaves of lettuce and a head of lettuce. And a jar of pickles. 1 pickle, I can actually get about 10 slices, 12 slices out of it, thick slices. So the limit here is my hamburger buns. I don't have enough hamburger buns for everything else. Hamburger buns limit the number of Big Macs that can be made. That's called the limiting ingredient. Now this becomes very important for these more complex problems as we had above. But today, my focus is going to be a process called dimensional analysis, not logic, to solve stoichiometry problems. The key to using my dimensional analysis is to understand the ratios of reactants and products. Ratios involved, then I'm going to use dimensional analysis, following the units. In the Big Mac example, we counted each ingredient. But when cooking pastries, pies, stews, soups, I'm dealing with mass and volume units instead. How many pounds of this? How many cups of that? And following the units becomes much easier, especially when I think about in chemistry, I'm dealing with atoms and molecules, which are very, very small. And we can't really see them well enough to count them. While cooking, I typically use ounces, pounds, cups, tablespoons, teaspoons, quarts, and gallons. Yes, this is the United States. Units of mass are ounces and pounds. Units of volume are cups, tablespoons, teaspoons, quarts, and gallons. But in chemistry, we use a metric system. The basic units in the metric system are the gram, liter, and seconds. The unit of mass is the gram, and we can use kilograms for very large masses, 1,000 grams, or micrograms, 1/1,000,000th of a gram for very small masses. The unit of volume is the liter, so we can use kiloliters, 1,000 liters, for very large volumes, or milliliters, 1,000th of a liter, for very small volumes. In this lesson, we're going to apply what we've learned about dimensional analysis and stoichiometry to a problem you will typically encounter in your chemistry class, the combustion of methane gas. Combustion reactions are exactly what it says. I'm burning an organic compound, usually a hydrocarbon. Now you know why I use the fire triangle as my image, because I'm going to be combusting something, burning something. And for that, I need oxygen, I need a fuel source. In this case, it's going to be a hydrocarbon, and heat. What are hydrocarbons, you say? Well, let's go back. Remember, the combustion reactions requires oxygen, fuel, and heat. You notice I've modified my fire triangle and replaced the word fuel with hydrocarbon, because that's the fuel that I'm going to be using within my examples. And a hydrocarbon is simply a molecule made of 2 types of atoms, hydrogen, thus the root hydro, and carbon, hydrocarbon. Remember, the carbon has 4 valence electrons, 1, 2, 3, 4. And with those valence electrons, it can make 4 bonds. One hydrogen attaches to each carbon bond site, bringing its own electron with it. This molecule that I drew is called methane, a hydrocarbon that contains 1 carbon atom and 4 hydrogen atoms. Note I'm using the old organic chemistry convention for naming this, methane. I'm using the dot structure, the Lewis dot structure for methane. In this, each dot represents 1 electron. 1 bond is made of 2 electrons. This is a bonding electron. In this case, 1 electron is being supplied by the carbon, and the hydrogen supplies the other electron. They're sharing the electrons. Because they're sharing the electrons, this is, if you recall, called a covalent bond. And this is a structural diagram for methane. Instead of 2 dots, a bond is represented by 1 line. If I have to draw a large molecule, a lot of these, this becomes a lot quicker and a lot easier. If I need to follow the electrons, I'm going to use a Lewis dot structure. Because I'm doing a combustion reaction, well, I'm just going to actually use the chemical formula. Here we understand how the carbon and hydrogens are bonded to each other, so we don't include the dots or the lines. Now let's get back to the stoichiometry of combustion reactions. So following our diagram, the reactants for combustion reactions of methane are methane, of course, CH4, and the molecule oxygen, which contains 2 oxygen atoms. Written in a chemical equation, the symbol plus means and. Methane and oxygen in the presence of fire. The arrow indicates the reactants will react with each other to produce something. Heat or fire is written above the arrow to indicate the energy is needed to start the reaction. So methane and oxygen are going to react together in the presence of heat to produce something. Typically, we don't write the word heat, but you draw a triangle as a symbol for heat or energy. But in this lesson, I'm going to leave the symbol off because it is a combustion reaction. We understand that we need heat already because we're dealing just with combustion reactions. But if the audience or who you're writing to doesn't know that this is a combustion reaction, we actually include the symbol itself. Now, a product of combustion of methane are carbon dioxide and water. In fact, those are the products of any combustion reaction. CO2, carbon dioxide, and water, H2O. But we see that during another example. Part of stoichiometry is getting the ratios, reactants, and products correct. We call that balancing the equation or making a balanced equation. I like the what do I know method. This means writing down how much of each atom we have for both reactants and products. This is very important because if I'm working in research or industry, someone's going to be writing down what their goal is, what their ideas are. And I got to go through that paper and then from there kind of annotate to say, okay, what do I know that they want? What do I know that they have in terms of using? In this case, I'm going to use a very simple tool called a 2x N table. 1 column for the reactants and 1 column for the products. In this case, N equals 3 because there are 3 different atoms, carbon, hydrogen, and oxygen. I'm not going to include N in terms of the headers. Next, I'm going to add the number in front of the atom symbol to represent how many atoms are shown in the common equation. Thus, what do I know? For the reactants, there is 1 carbon atom, 4 hydrogen atoms, and 2 oxygen atoms. 1 carbon atom is in the methane, 4 hydrogen atoms are in the methane as well, and of course the 2 oxygen atoms come from the oxygen molecule. What do I know about the products? There's only 1 carbon in the carbon dioxide, 2 hydrogens in the water molecule, and 3 oxygens combined, 2 in the carbon dioxide and 1 in the water molecule. Now, is this balanced? That means do I have the same number of atoms, all types of atoms for the reactants and products? So let's check the carbon atoms. Wait a minute, there's 1 carbon reactant and 1 carbon product. Isn't that balanced already? Well, I'm just going to go through the process for each step by step just to be cautious. Now, in my reactant, I have only methane that carries a carbon. There's 1 of those. For the products, carbon dioxide is the only molecule that carries a carbon, 1 carbon. So I see the carbon atoms are balanced on both sides of the equation. Now let's check the hydrogen atoms. I see that the methane is the only molecule in the reactants that has hydrogen. There's 4 of those. Water is the only molecule in the product side that has hydrogen, and there's 2 of those. I see that my hydrogen atoms are not balanced. What do I do? Take a moment to figure out what you would do. While you're doing that, remember this is not a balanced reaction. We're going to go from carbon to hydrogen next, leaving oxygen to last because that's going to make the process easier. If you notice, there is only one molecule that contains oxygen on the reactant side, and that's oxygen molecule. It only contains that one atom. So if I leave that to last, then any changes I need to do to balance that, I can do. While on the product side, I see that oxygen's in 2 different molecules, carbon dioxide and water. So by doing that last, all I have to do is whatever I did to balance the carbon and hydrogen, and however affected the oxygen on the product side, I just need to simply mathematically manipulate the oxygen on the other side to get it balanced. And to do this, I'm going to use a method I learned from math, cross multiplying. Do you remember cross multiplying? We use that here because we're going to multiply the molecules of either reactants or products until the numbers of atoms are balanced. Just like a bicycle, if I'm going to build that, I'm going to bring over a bicycle wheel. Now, a bicycle wheel is made of several different components, but to build a bicycle, I need a whole bicycle wheel. I'm not going to be balancing number of spokes on both bicycles. I need a whole wheel for that bicycle. Now, a quick review of my cross multiplying. Do you remember this problem from your math classes? 1/2 plus 2/3. What's the answer? I can't just add these together because you notice denominator are different. Denominator for 1/2 is 2, and denominator for 2/3 is 3. So what do? I'm going to cross multiply. In other words, I'm going to multiply the 2 by 3. And remembering that a number divided by itself is always equal to 1, so all I'm doing is change the form of the fraction. I'm not really changing the fraction. So I'm going to multiply 1/2 by 3/3. That gives me 3/6. 3/6 and 1/2 are really the same fraction. And I'm going to multiply 2/3 by 2/2. That gives me 4/6. And 4/6 and 2/3 are also the same fraction, just in a different form, a different denominator. But now that my denominators are the same for both of my fractions, I can just add the numerators. 3 plus 4 is 7. Thus my answer is 7/6. You notice I made the change to the whole fraction. I want to do the same thing for the molecules. I want to make the change to the entire molecule, and it's going to change all the different components within it. Just as I change 1/2, I change both the numerator and denominator. So I'm going to cross multiply for my hydrogen. So if I multiply the product of water by 2, what do I have for hydrogen? Well, there's 2 hydrogens in water already. If I have 2 water molecules, well, 2 times 2 is 4. Now, my hydrogen and carbon atoms are balanced. 1 carbon on the reactant, 1 carbon on the products, 4 hydrogens on the reactants, and 4 hydrogens on the products. Now let's move to the water molecule. And let's look at the oxygen. Now on the reactant side, there's only oxygen in the oxygen molecule, and that's 2. On the product side, as I said before, there's oxygen in the carbon dioxide as well as the water. I have 1 carbon dioxide that's carrying 2 oxygens, so that's 2 there. I now have 2 molecules of water, and there's only 1 oxygen in the molecule of water, so that's 2. 2 plus 2 is 4. So I have 4 oxygens on the product side now, after balancing my carbon and balancing my hydrogens. Now, how do I balance oxygen? What do I do with the oxygen molecule? Take a moment and see what you will come up with. Now, as you notice, the oxygen atoms are not balanced. But if we simply double the amount of oxygen molecules, multiply it by 2, now I have 4 oxygen atoms on the reactant side, as well as 4 oxygen atoms on the product side. Now my oxygen atoms are balanced. I'm done. But I always want to make sure I did not make a mistake. So let's recheck. What do I know now? Based on my chemical equation, I have 1 carbon on the reactant and 1 carbon on the product. My carbon atoms are balanced. I have 1 hydrogen atom on the reactant, 4 hydrogen atoms on the reactant, 4 hydrogen atoms in the product. My hydrogen atoms are now balanced. I have 4 oxygen atoms on the reactants and 4 oxygen atoms on the products. My oxygen atoms are now balanced. This is now a balanced equation. Congratulations, you have balanced a combustion reaction involving methane. Next time we're going to look at another hydrocarbon that will make this a little bit more challenging. Until then, take care.